In this video, we're going to look at confidence intervals for the population mean. Now, the logic for constructing a confidence interval for a population mean is the same as the logic for constructing a confidence interval for a population proportion. We need to find a point estimate, we need to find the margin of error, and then if we take the point estimate minus the margin of error, and if we take the point estimate plus the margin of error, then that will give us our confidence interval. For a population mean, though, the point estimate is going to be the sample mean. So if we're going to be estimating the population mean mu, then we're going to do that by using a sample mean, x bar. The margin of error, E, should be defined as the difference between the predicted mean, x bar, and the actual mean, mu. And this is the same logic that we used for population proportions. So the error should be the difference between the point estimate, x bar, and the parameter, mu. Well, using the same argument that we used for proportions, we know that if we have a normal distribution, then the z-score is equal to x minus mu over sigma. Well, for an x bar distribution, that would be z equals x bar minus the mean of the x bar distribution divided by the standard deviation of the x bar distribution. But we know that for an x bar distribution, the mean of the x bar distribution equals the mean of the population, and the standard deviation of the x bar distribution equals the standard deviation of the population divided by the square root of the sample size. So this is the mean and the standard deviation of an x bar distribution. So what we really have here is that z equals x bar minus mu, again because the mean of the x bar distribution equals mu, divided by sigma over the square root of n, again because we know that the standard deviation of the x bar distribution equals sigma over the square root of n. So notice what we have on top here. We have x bar minus mu, which is what we said the error should be. So that means that x bar minus mu should equal some z-score times sigma over the square root of n. And this is perfectly true. This would be the calculation for finding the margin of error for a confidence interval for a population mean. There's only one issue with this formula, and that is right here, sigma. The trouble is we're never going to know what sigma is. We're never going to know that. If you'll remember, we had that same issue when we were dealing with proportions back in the previous section. Our formula should have been E equals z times the square root of p times 1 minus p over n, but we would never know what p is, and we had to use p hat in its place. Well, using p hat in its place works just fine. That doesn't cause any huge issues. Well, in the same kind of way here, we could use s in place of sigma, use the sample standard deviation in place of the population standard deviation. So that is, we would get E equals z times s over the square root of n. The only trouble with that is because we're using s instead of sigma, this causes additional variability. And the amount of additional variability that's caused by using the sample standard deviation instead of the population standard deviation is more significant than it was whenever we used p hat in place of p when we were dealing with proportions. So this is a bigger issue, and we have to contend with this. So to cut to the chase, what it boils down to is that when we use s in place of sigma, what happens is we no longer exactly have a normal distribution unless the size of the sample is really big. So for most practical purposes, we're not going to be able to use the normal distribution. In other words, we're not going to be able to use z here. So instead, we're going to use a new type of distribution that we're going to need to define, and that's called a student's t-distribution. So I'm going to go ahead and say this. It's not going to quite make sense until we look at what a t-distribution is. So what has to happen is this z-score has to be replaced with something new called a t-score. So our margin of error isn't going to equal z times s over the square root of n. It's going to equal a t-score times s over the square root of n. And we're going to call that t-score t sub alpha over 2 instead of using a z sub alpha over 2. So this is going to be our margin of error calculation. And again, it'll make a little more sense once we understand exactly what a t-distribution is. So let's talk about that now. So student's t-distribution. Suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t equals x bar minus mu over s over the square root of n follows student's t-distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. So look at this definition. If I pull back in my previous sheet, so here I had z equals x bar minus mu over sigma over the square root of n. So that was the z-score whenever we were dealing with an x bar distribution. Well, the only difference between this z-score statement that I have right here and this t-score statement that we have right here is that we have s in place of sigma. And again, that substitution of s in place of sigma causes additional variability, and that's why we now have this t-distribution instead of the standard normal distribution. So, a couple of other things about the t-distribution. First of all, what's this business about n minus 1 degrees of freedom? Well, if you'll remember, we talked about degrees of freedom once before when we talked about calculating the sample standard deviation. If you'll remember the formula for calculating sample standard deviation, it is that s equals the sum of each data value minus the sample mean squared divided by n minus 1, and then we took the square root of all of that. Well, that n minus 1 that we were dividing by was the degrees of freedom. So let's think about what degrees of freedom are. Well, the degrees of freedom of a point estimate is the number of independent values that go into calculating the estimate. What does that mean? Well, another way of saying that is that the degrees of freedom are the number of values that can vary when we're calculating an estimate. For example, to try to help this make a little more sense, suppose you want to pick 4 numbers that's going to have an average of 50. So pick 4 numbers that average to be 50. Now think about that just for a minute. What are the possible 4 numbers that you can pick that will have an average of 50? Well, let's call those numbers x1, x2, x3, and x4. So we're going to add those 4 numbers up, divide by 4, and we want the answer to be 50. So again, my question is, what could those 4 numbers be? Well, they can vary a little bit. So for example, what if the first number is 49, and the second number is 51, and the third number is 52? So if I'm going to add those 3 numbers up plus the 4th number and divide by 4 in order to get an average of 50, well, the only way that I'm going to get an average of 50 is if this value right here is 48 for these these numbers that I picked. So my point is that even though I had 4 numbers, once I've chosen these 3, the value of that last number is no longer free. The value of that last number has to be 48 in order to get an average of 50. So if I have the restriction that these numbers are going to average to be 50, even though I'm adding up 4 numbers, only 3 of them can vary. The 4th number can't vary. The only way that I'm going to get this average in this particular case is if this last number is 48. In the same way, suppose the first number is 45, the second number is, let's say, 56, the third number is, let's say, 47, and then if I'm going to get this to average to be 50, the only way that can possibly happen is if that last number is 52. So again, if this last number is anything other than 52, then this isn't going to average to be 50. So again, even though I have 4 values that I'm adding up to get an average of 50, only 3 of those values can really vary because that last value is going to be determined by the previous 3. Otherwise, we're not going to get this average of 50. So in the same way, instead of adding up 4 values, suppose I'm adding up n values. So if I have x1 plus x2 plus x3 and so on all the way up to n values, and I divide by n, well, if that's going to have a specific value, say mu, then even though there are n values, only n minus 1 of them are going to be able to vary. That last value, that nth value, is going to be predetermined by the previous n minus 1 values if we're to get this mean. So that's the idea behind degrees of freedom. Now let's look back a little bit more at this notion of a student t-distribution. A student t-distribution has specific properties similar to those of the normal distribution. So, properties of the t-distribution. The t-distribution is different for different degrees of freedom. So the specific shape of a t-distribution is going to depend on the degrees of freedom. 2. The t-distribution is centered at 0 and is symmetric about 0. 3. The area under the curve is 1. The area under the curve to the right of 0 equals the area under the curve to the left of 0, which is equal to 1/2. 4. As t increases or decreases without bound, the graph approaches but never equals 0. So in other words, the t-distribution is asymptotic to the horizontal axis, just like the normal distribution was. 5. The area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution, because we are using S as an estimate of sigma, thereby introducing further variability into the t statistic. And last but not least, 6, as the sample size n increases, the density curve of t gets closer to the standard normal density curve. This result occurs because as the sample size increases, the value of S gets closer to the value of sigma by the law of large numbers. So in other words, as the sample size goes up, the degrees of freedom are going to go up, and as that happens, the t-distribution becomes more and more like the actual standard normal distribution. So the main thing that you want to understand is that if we have the standard normal distribution, so for example, if this is the standard normal distribution, student t-distribution is going to be quite a bit like this, except in student t-distribution there's more area in the tails and less area in the middle. So if this is the standard normal distribution, the t-distribution is generally going to be a little shorter and have a little fatter tails. Pull in one last sheet here. So here are some graphs of both the standard normal curve and a couple of t-distribution curves. So if you take a look at this graph, the graph in blue is the standard normal distribution. So we can see that right here. I'll outline it. So this curve right here, it's in blue now, but I'm going to outline it in black. This is the standard normal curve. And so it is going through here like this, and it's going through here like this. Well, again, to compare what a t-distribution looks like, you can see the orange curve here, which is this one here, comes under, and it's the shortest one here. This is a t-distribution where the sample size is 5, which means there's 4 degrees of freedom. So again, if you compare that to the normal distribution, it looks a lot like the normal distribution. It's just got fatter tails and it's shorter in the middle. So there's more area in the tails, less area in the middle. Well, if you look at the pink curve, which is this one in the center here between the orange and the original blue, well, this is a t-distribution where n equals 15. Now, if n equals 15, that means there are 14 degrees of freedom. So the pink curve there in the middle is a t-distribution with 14 degrees of freedom. So notice that it has more degrees of freedom, so it is closer to the normal distribution. There's less distinction between the pink curve and the original blue curve, the normal curve. So this is the idea. As the degrees of freedom go up, as the sample size goes up, there's less distinction between this t-distribution and the standard normal distribution. So we're going to be using this t-distribution as we construct confidence intervals for the population mean. And so in the next video, we're going to look at the t-distribution a little more closely.